Tangents and normals is what we've been looking at. Yesterday, we used the parametrics idea to solve the problems. Now I'm going to do it from a traditional Cartesian way and do some of the same problems. So our tangent, again, it still has the equation x squared equals 4ay. But now I'm just going to give it traditional coordinates x1, y1. So we still do it the same way, of course. We've got to differentiate y. There it is, x on 2a. But this time the gradient is x1 on 2a. Put it into our point slope formula, y minus y1 equals m outside of x minus x1. Multiply by 2a. Something interesting happens. There's the equation. Well, hang on, I'll get it to the form we usually write it. And you'll notice I've written it in a very strange way. Instead of writing it as something x plus something y, look at how I've written it. x1 is equal to 2a y plus y1. I've written it that way very deliberately. Have a look at the equation of the parabola. X squared equals 4ay. Now have a look at our answer. Now, x1, if the 1 wasn't there, you'd say, well, x times x is x squared. And then look at the other side, 2a, y plus y1. Again, if that little 1 wasn't there, you'd go, oh, y plus y is 2y, and you get x squared equals 4ay. So the actual equation of the tangent is very similar to the equation of the parabola itself. It still has that feel of x squared equals 4ay. It's just that one of the y's is a coordinate, so we call it y1. It's an interesting feature, and it actually happens for all of conics, all the different conic shapes. It works when you're doing tangents to ellipses, tangents to hyperbolas, circles, all of them turn out that way. All right. I'd like to say something equally nice happens with the normal. I'd like to say that. Okay, there's our point. Our normal, of course, is at 90 degrees. So now, if we know the slope of the tangent is x1 on 2a, slope of our normal will be minus 2a on x1. Put it into our point slope formula. Let's see what happens when we play around with this one. Now, this one, I have put the x and the y together. So we do get a sort of a pattern there. So you notice on the left-hand side, when I've just left it with the pronumerals, I get 2a x plus x1y. On the right-hand side, where I use the coordinates, I get that same pattern, 2a x1 plus x1 y1. So there is some sort of pattern to it. It's probably not as nice, I think, as the tangent one, but it's a pattern. Okay, let's look at this idea of lines cutting, touching, or missing the parabola altogether. So there's our parabola. So to say, if I was to draw a line, it could do one of three things. It could cut through the parabola, it could touch the parabola, or it could miss it altogether. So I'll just give it our general form, y equals mx plus b. Now if I was to say to you, find the point of intersection, well, we'd solve them simultaneously. So let's do that. X squared equals 4a, but instead of y, I'm going to write mx plus b. And I can create a quadratic equation, x squared minus 4amx minus 4ab equals 0. Now, with our knowledge of the discriminant, we can come up with a condition for it to cut, touch, or miss, because the solutions will be the number of times that it cuts. So I'm not actually interested in the solution. I'm more interested in how many solutions there are. And that's where the discriminant's really good. I know there'll be two solutions. In other words, the line cuts the parabola. I know there'll be two solutions when the discriminant is greater than 0, because there'll be two solutions to the quadratic equation. I know there'll be one solution, and this idea, of course, we use quite a lot. This idea of, is something a tangent? We can say, well, if there's one solution to this quadratic, then the line must just touch the parabola. So there's one solution. Discriminant is equal to 0. And it'll miss it altogether if there's no solutions. So discriminant is less than 0. So I don't need to solve the actual quadratic itself. Let's have a look at the discriminant. Discriminant b squared minus 4ac. So we get minus 4am all squared minus 4 times 1 times minus 4ab, and I end up with 16a outside of am squared plus b. So I could have a condition which simply says, well, I know there's going to be two solutions when am squared plus b is greater than 0. Yes, the discriminant was 16a times that, but remember, I'm looking at my concave up parabola, so I know a is going to be positive anyway. So it's going to be the thing in the parentheses that's going to decide whether the whole thing is positive, negative, and so on. So am squared plus b is greater than 0. It'll touch when it's equal to 0. That, as I say, that idea of discriminant equals 0, come up with a lot. And miss when it's less than 0. Now, it's not like this is a formula we need to know. It's more the idea that's important. So you'll see questions which will say, yeah, prove that if this is a tangent, then this condition will hold. And so the idea is, all right, let's have a look at the discriminant when we solve these simultaneously. Here's the same question as yesterday. Yesterday I did it using parametrics. Today I'm going to use the Cartesian idea. Now I know the tangent will be of the form y equals mx plus b. So therefore 2 equals 3m plus b. Because I know the point 32 is on the tangent. It's on both tangents. I'm going to rearrange that and make b equal to 2 minus 3m. Okay. So my tangents, remember, are going to be y equals mx plus b. But instead of b, I've just got 2 minus 3m. So now, if all I can work out is the slope, that what m is, I can find the equation. I just got to substitute the m in. So how do I do that? Well, x squared equals 4y. I'll substitute in the line mx plus 2 minus 3m, and I can create a quadratic. But remember, I don't actually need to know what x is. I'm interested in knowing what m is. And so I can say, well, look, if it's a tangent, I know the discriminant is going to equal 0. So b squared minus 4ac will equal 0. Solving this equation, actually we can tidy that up. 16 goes into everything. There we go. Two possibilities. Either m is 1 or m is 2. Now I can go substitute back into our equation of a line. So therefore we get y equals x minus 1, y equals 2x minus 4. So same question as yesterday, but instead of using parametrics, I've used a Cartesian idea to solve the problem. All right, 9g. Whoa, it's gone. Backwards 9g. No, forwards 9g. There we go. We shall play with those ideas.